I'm calling Lecture 1a. It's the first of a series of lectures that are produced by myself and Andrey Alenin, who are putting together the two sections of the course on plane wave propagation and on waveguides. So today what we're going to do is we're going to start talking about fields and source quantities, relate this ultimately to plane wave propagation, reflection, refraction, and then we're going to go into the types of structures that are used to guide waves. As part of this conversation over the course of the next 6 weeks, we're going to link back to what you learned about transmission lines and talk about how the field quantities that we teach in electromagnetics are related to the circuit quantities that you're much more used to be dealing with. So as a starting point, let's talk about what the objectives are for this course. And I want to try to be extremely consistent with you guys throughout the course of this section so you can understand what are the major takeaways from each of the lectures and how are you going to be tested on it. So not only what is the objective, but to what level of depth are you expected to have comprehension of the material. So there's two principal objectives that come from this class, this lecture. The first is we want to know the principal field quantities of electric and magnetic field, what their units are, how they're related to macroscopic circuit quantities that you're more used to dealing with, like voltage and current. How well should you know this? Well, you should know it really well. You should have complete command of the field quantities. You should be able to use their units to help in dimensional analysis, and you should have a really good feeling by the end of this class about how these field quantities ultimately relate to things that are important, like the currents flowing into an antenna, the reflection from a lens, or the voltages and currents that might flow in a circuit. The second major topic that we're going to touch on today is understanding the concept of electric and magnetic flux. And so you've seen fields before. You would have seen fields pretty extensively in your Physics 1b class. It's been a couple of years. But today we're going to start talking about the concept of flux, how the fields are related to flux, what flux means, how flux is related to the sources, and how fluxes couple into circuit parameters such as capacitance and inductance. How well should you know this? Well, you should be able to comprehend the relationships between fluxes, fields, and sources in the context of how they relate to circuit quantities and fields problems. So let's start off by talking about the major field and source quantities that we're going to be dealing with for the rest of this semester. First field quantity we're going to be looking at is the electric field intensity. It's denoted with the E. We're going to stick with the notation that we've been using so far. So we use this script E with a bar over it, which indicates that it's a vector field. This electric field has units of volts per meter, and we call the electric field intensity. Over here in this picture, we see these electric field lines, which start at one conductor and go to the other conductor, and those are our electric fields. We also have magnetic field intensity. So whereas this script E denotes the electric field, this script H with a bar over it is the magnetic field. It's related to current. Okay. And we have the magnetic field intensity as units of amps per meter. Right? So I didn't mention this before, but this voltage is, we can do an integral of the electric field dotted into the path. And so if I integrate from one conductor to another, whoops, get rid of that. If I integrate from one conductor to another, that's my path. Okay, that I'm going to integrate along, and I take the dot product of the electric field times this path, and I integrate from one point to the next. That's going to give me the potential difference between 2 points. Okay, so we'll talk a little bit about potential, and we'll use potential more clearly throughout the rest of this course. Likewise, Ampere's law, which we'll talk about in a couple of days, allows us to relate the magnetic field to the current. So if I integrate around a closed path, okay, then the integral around that closed path is equal to the current that's flowing on the wire. And so in this case, we use the right-handed rule. So I take the integral of H. I'm going to have current that's actually flowing into that conductor in this case. So my eye is going to be going into the screen. So in addition to these two quantities, we've also got fluxes. The first quantity is D, which is I call the electric flux density. Many people call it the displacement field. Depending upon how you're using it, those two names have particular meanings. So when we use D in the context of materials, displacement relates the displacement of the positive and negative charges in, say, an insulator. But I like to use it as the electric flux density because of the symmetry. The D vector has units of coulombs per meter squared, and as we're going to see, coulomb is the unit of charge. So if I come over here to a capacitor, I've got, say, positive charge on the top of the capacitor, negative charge on the bottom of the capacitor. That sets up flux in between, and the quantity of flux, the total flux in this capacitor, electric flux, is equal to the Q that's separated in this particular step. So if I have plus Q total charge on the top and minus Q total charge on the bottom, okay, that total charge separation is equal to the flux, which is equal to the capacitance times the voltage. Likewise, I can have a magnetic flux density. So if I've got a current flowing around a loop, right? So in this case, I've got my current flowing in this direction around the loop. Okay? That current is going to generate a flux, and again, by the right-hand rule, the current flows this way, and the magnetic field will rotate around it. Okay? So my magnetic field is going to come up through the inside and then come back down around the outside, and likewise on the other side. Okay? Those are my magnetic fields. And if I take a look at the total flux, I take the integral of B dot dA around this inside the loop, that's going to give me the magnetic flux. And that magnetic flux is equal to the inductance of the element times the current that's flowing in the element. Okay? Some very important unit conversions, and units are fundamental. When you understand the units of a quantity, it helps you understand the physics, and it can also tell you where you're making a mistake in a problem. So watts, which is the unit of power, where we know that's equal to a volt times an amp, or a joule per second. Right, so fundamentally, a watt is how many joules per second are you providing to your circuit, or are you dissipating in your circuit? And it's the voltage times the current. A joule, of course, is a Newton meter, a force acting over a distance. But in the context of electrical circuits, it's a capacitance times a voltage. A Weber, which in principle is the unit of magnetic charge, is equivalent to a volt times a second, or an amp times a Henry, right? So we have this Weber, which is the unit of total magnetic flux, okay? And that's L Henries times I amps. Likewise, my capacitance, or my coulomb, C, right? So this is a coulomb charge. That's an amp times a second, or an amp can be thought of as a coulomb per second, and that's equal to a voltage times a capacitance, right, as we got in this relationship here. And so these are important to understand when you're working a problem, to see how the units of electromagnetism are related to the units of Newtonian mechanics, right? Because a watt in Newtonian mechanics is the same as a watt in electrical systems. And of course, when you go on and learn about electrical power generation, what you're going to do is you're going to convert some mechanical energy, right, into electrical energy that you can use and transmit. Talk a little bit about sources. The fundamental source quantity that we're going to be dealing with is the electric charge. The electric charge, which we'll use as Q, can either be positive or negative. It has units of coulombs. As by way of reference, the charge on the magnitude of the charge on a single electron or proton is 1.6 by 10 to the minus 19 coulombs. And of course, an electron has negative charge, whereas the proton has positive charge. They're equal and opposite. The total charge in, say, a hydrogen atom, which has a proton, a neutron, and an electron, the total charge on a hydrogen atom, which has a proton and an electron, if it has a neutron, it's deuterium, is 0, because you have a positive proton, a negative electron, and those two in a macroscopic sense cancel each other. Now, in this class, we're going to be often interested in distributions of charges. And so if I have a total amount of charge Q, right, and I distribute that total charge Q over a length L, that gives me a line charge density, rho sub L. that has units of coulombs per meter. So I take rho, if rho is a constant, multiply by the length, and that gives me the total charge Q. If I took that same total charge Q, and now I distribute it across an area, okay, I now have coulombs per square meter, and that is a surface charge density, rho sub s. And if I take that same amount of charge Q, and now I put it in a volume V, I'm going to have a volume charge density of coulombs per cubic meter. Likewise, I can have current. Right? When I have a charge Q and that charge starts to move, and I'm sitting at one point in space and I count how many charges go past me in a given unit of time, I'm going to have a certain number of coulombs that are going to go past every second. And a coulomb per second is an amp. Right? So if you have 1 amp current, that means a coulomb of charge has moved past the point of observation in each second. And so that is fundamentally this unit I, or this quantity I. It's current, it has units of amps, and here I can see I have a current I flowing in a wire. In this case, we'll assume that the wire has 0 area, so all that current is flowing through. We'll treat this as a simple ideal line. Of course, in many problems, I may have a surface, right? So I may have metal on one side of the surface and air on the other side of the surface, and I get a current that flows along the interface. It doesn't flow inside, it just flows on the interface, if this is an ideal perfect conductor. Okay? And so in that case, I'm going to have a total current I, okay? But that total current I is flowing over, get rid of that, sorry, that total current I is going to be flowing over, in this case, say a width W, right, as the current is flowing out of the page, right? And so that's going to give me a surface current density, has units of amps per meter. So if I have 1 amp per meter flowing on a surface that's 1 meter wide, I'm going to get a total of 1 amp flowing in this direction. And of course, I can also have a volume current density. If I take that 1 amp, now, and I distribute it across this volume, so I have all my current flowing out of the page like this, that's going to give me my current density. It says here volume current density, but we typically just call it the current density, and that's going to have units of amps per square meter. Right? So I, a current flowing on a line, is an amp. Surface currents are flowing on the surfaces of conductors, amps per meter. Volume currents have units of amps per square meter. The last couple of important points that I want to emphasize. One is conservation of flux. Right? So we've already made note of the fact that the units on the electric flux density, D, are coulombs per square meter. That's equivalent to a charge density. Right? So if I were to take a closed surface, I'm going to make a sphere, and I'm going to integrate all the flux that comes out of that sphere. And so that's what this notation indicates. I'm integrating over a closed surface, d.ds, so the outward flowing flux. Okay? There's a relationship known as Gauss's law, which tells me that the net electric flux flowing out of a closed surface is equal to the total charge enclosed inside that surface. So my total flux is equal to my total charge. Okay? Now, I can do some mathematical tricks. Right? I know that from my calculus classes that this particular surface integral is equal to, by the mathematical relationship Gauss's law, the volume integral of the divergence of D. Right? So I've got a surface S here that encloses a volume V, right? And so the integral of the flux penetrating through that surface, well, that's equal to the integral of the divergence of the flux inside the volume. Okay? Well, we know this quantity on the left is equal to total charge enclosed. And we know that the total charge enclosed is equal to the volume integral of the surface of the volume charge density. Okay? So over here, I've got the left-hand side of those are equal, right? That means that the right-hand sides had to be equal. And importantly, this must be true for any volume. So because that must be true for any volume, the only way that can be is when these two integrands are equal. And I have that the divergence of D is equal to rho. And so this is a very important concept. What this tells us is that if I go to any point in space, if the divergence of D is 0, then I can't have any charge there. That means that that flux line must be continuous. If that flux line isn't continuous, that means I must have a charge present at that location. Now, since there are no magnetic point charges, that tells me that magnetic flux lines cannot begin or end. They must be conserved, and the divergence of the B field is equal to 0. And this is something that we're going to leverage later on dealing with more complicated electromagnetic problems. The last thing I'm going to do in this lecture is to relate some of the electromagnetic field properties to some laws that you already know. Now, we know that current is equal to the amount of charge crossing a surface per unit time. And if I take that surface as a closed surface, okay, then the amount, if I have a net amount of current flowing out of that closed surface, that means that the amount of charge inside that surface must be decreasing. So I have the net positive flow of current out of the surface. Here's my surface S. And I have a net positive current flow out. Okay. Then the charge inside must be decreasing. Okay. This ends up being related by some math. Well, we know from Gauss's law that this integral is equal to the divergence. The integral over the surface is equal to the integral over the volume of the divergence. We know that this time derivative q, well, that's equal to the integral of the volume of the time derivative of the charge density. Right? And so equating this left-hand integral with this right-hand integral over an arbitrary volume v tells us that the divergence of J is equal to the time rate of change of the charge density. We call this the continuity equation, and it's an important auxiliary equation in electromagnetics. It's related to Kirchhoff's current law. Right? Kirchhoff's current law tells us that if I have a circuit, oops, sorry about that. Kirchhoff's current law tells us that if I have a circuit and I have a current flowing into a node, right, and this is I1, this is I2, and this is I3, Kirchhoff's current law tells us that the sum of I1 and I2 must be equal to I3. That is a macroscopic statement of the equation of continuity. The other major circuit law that you apply all the time is Kirchhoff's voltage law. For static fields, we can write the electric field as the gradient of the potential, and we'll talk a little bit about potential later on in the course, but we'll just take this today as given. Well, there's a relationship, there's a mathematical rule that any field that's written as a gradient has no curl. So when I take the curl of a gradient, that is always equal to 0, and you can demonstrate that to yourself. It is a mathematical representation. Any field that can be represented as a gradient has no curl. Okay. Well, Stokes' theorem relates these two integrals. If I have a path integral of the electric field around a path, that is equal to the integral of the curl over the area. So if this is my path, that's my path L, and I take the path integral of E dot dl, okay, that path integral is equal to the surface integral of del cross E dot ds. But we already said that the curl was equal to 0. Right? So since the curl is 0, this second integral must be equal to 0, which means that this integral must be equal to 0. Okay? So that tells me if I integrate the electric field around any closed path, that's equal to 0. Well, that's Kirchhoff's voltage law, right? I have a resistor, and I have a voltage source. When I integrate, when I go around here and I have voltage, in this case a voltage drop across this source, it means I need to have a voltage rise here, and it's going to tell me what direction the current's going to flow, and that's my KVL. And of course the last and potentially most important of the circuit laws is Ohm's law. Ohm's law you know as V equals IR, right? So Ohm's law, you've known it for years, and it tells me that V equals I times R. Well, I'm going to convince you today that that's the same thing as saying that J equals sigma E. So let's assume that the field is constant. Right? So I have a voltage. That voltage is equal to the electric field times the length of the wire. Right? So the voltage drop across the wire is equal to the magnitude of the electric field times the length of the wire. The current that's flowing across that wire, well, that's equal to the current density, J, times the area. But J is equal to sigma E. Right? So the resistance in this wire is the voltage divided by the current, and that's equal to L over sigma A. Right? The way that I get to this relationship is that when I apply an electric field, these charged particles are going to accelerate, but they're only going to accelerate so far, then they're going to bounce off of something. So I have electrons flowing. They're eventually going to hit the positive charge centers, and then they'll stop. They'll be reaccelerated, and then they'll stop. Then they'll be reaccelerated again. They have an average velocity, which is related to the mobility. The total current is equal to the charge per carrier, so if they're electrons, minus 1.6 by 10 to the minus 19 coulombs, times the average velocity, times the number of electrons per unit volume. And that gives me the total current. I can group these quantities together, and that's what the conductivity is. So that brings us to an end of this first lecture. In the tutorial topics that we're going to go over in our next class on this subject here, and you have these tutorial questions, there are a few things that we touch on magnetic sources, what they might mean, what their units might be, how we might think of them. We're going to work with charge and current distributions. How do I relate volume and surface charge distributions to total charge? We're going to look at the macroscopic and microscopic versions of Ohm's Law in order to compute bulk resistance. And finally, we'll look at the difference, the relationship between potential difference and the electric field. So I hope you enjoyed this lecture. You can take a look at my notes, you can take a look at Wentworth, you can review these slides, and then you can take a stab at the 5 tutorial questions, and we'll touch on those tutorial questions when we get to class on Tuesday.